Hi everyone and welcome to my YouTube channel. We're continuing our inequalities playlist. In the previous video, we started with algebraic tricks. We started with the very famous Ravi transformation. And in this video, we'll be continuing with other algebraic tricks. Today we'll be discussing the substitutions, substitutions basically strategy. And we'll be discussing some manipulation techniques as well. Alright, so what are you waiting for? Let's get started. Alright, so our first example is basically kind of a review of a technique that we learned before. So as we said, like sometimes when solving an inequality, we have a condition. And of course, our goal is to get rid of the condition. Sometimes you can solve the question by like somehow using the condition without really getting rid of it. But basically what we're learning in this kind of like lesson is how to get rid of these conditions. So one very important technique is homogenization. We already learned that in the AMGM video. So first of all, let's just do like a quick review of this technique by discussing the following example. So here we just given A, B, C, positive real numbers, and their sum is 1. So we have this condition here. And we're asked to prove this inequality here. Okay, so we have a condition, we want to get rid of it. Let's homogenize. How do we homogenize? As you can see, this thing is degree 1, this thing is degree 2. So you want to make them the same. What's the easiest way to make them the same? To make this degree 2, right? We want to make this degree 2. How can we do that? Since this is degree 1, this is 0, we can just like here multiply by sigma a, right? If you multiply this by sigma a, then now this is degree 2, this is degree 2, so this thing is degree 1. So all of the LHS is degree 1. The RHS is degree 0. To make it degree 1, you just multiply by sigma a. Alright, so now we homogenized everything. So we can just prove instead A times A plus B plus C plus BC is less than 2 sigma A. Now we can forget totally about the condition and we can start proving this. Okay, so let's do that. So first of all, as you can see here, we have this thing. Let's expand it. It's basically a square plus AB plus AC plus BC, so it's sigma AB less than 2 sigma A. Alright, now this thing here should be familiar to you. This thing is very famous. It can be factorized. Of course, this thing is sigma A plus B times A plus C. Alright, now this thing is nice. Now, of course, how can we deal with this inequality here? This thing is the ugly thing, so let's try to fix it. What inequality can we apply here? We want to maximize this. How can we do that? As you can see, this thing here is just like sigma and like something like this, sigma xy, right? Product of stuff. And we know to maximize this, we have Cauchy. Cauchy is very like important to maximize this. So we can just say that the LHS is less than, and by Cauchy, of course, going to have a big like square root, sigma this times sigma this. What's sigma A plus B? Let's just write it first. Times sigma A plus C. And that thing here is equal to 2 sigma A here times 2 sigma A, which is equal to 2 sigma A. And we're done. That's it. So basically, this is a very standard question about homogenization. Homogenization is like a very important technique in order for us to get rid of the conditions in general. However, is this like the only technique that we can use? Well, let's see. Okay, so for this example, this one is an IMO question, IMO 2000, problem 2. As you can see, we're given ABC positive, and we were given this condition, ABC equals 1, so their product is 1. And we need to prove the following inequality. This thing here is less than 1. Okay, so let's say we have a condition, we want to get rid of it, so we want to homogenize. Well, how exactly can we homogenize here? If you look at this thing is degree 1, this thing is degree 0, this thing is degree -1. Here you have degree 3 is equal to a degree 0 thing. So if you look at this, it's a little tricky. Like, how exactly can you homogenize this? So what can we do here? Well, it turns out that there is a very beautiful substitution for this case, for this case in general. Whenever like you have ABC equals 1, product like of three numbers equals 1, then you can use a very famous substitution. And by the way, you can use it without proof because it's very famous and it's very like logical and easy to prove actually. So let's say we're given 3 ABC or three numbers such that their product is 1. Then there exist 3 positive real numbers x, y, z. It's kind of similar to the rapid transformation, such that A is x over y, and B is y over z, and C is z over x. As you can see now, if you like multiply them, A, B, C, going to cancel like x with x, y with y, and z with c. So indeed, like their product is 1. And of course, like it's very easy to prove this. So if you just let like A and B be like x over y, y over z, then you can easily see that C should be c over x. Okay, so using this, actually, you can just get rid of this condition, and you can now homogenize it by force. So, as you can see, this is like the core idea of the substitutions. Substitutions are very important, and this one is a very famous substitution. Okay, so right now, let's just do that. So, we can just say, first of all, there exist x, y, and z that are positive, such that A is x over y, B is y over z, and C is z over x. Now, our inequality, we can write it in terms of x, y, z is the same as like the product by of x over y minus 1 plus, okay, the inverse of this is z over y. This is less than 1. Okay, now clearly you can multiply by y here. In fact, everything by x, y, z, I'm going to get. Okay, so the y here is going to give us just pi x plus z minus y is less than x, y, z. Alright, so now we just need to prove this. As you can see, degree 3, degree 3. Very nice. Now everything is homogenized, and we got rid indeed of this condition. Okay, now if you look at this, this should be familiar to you. In fact, we just discussed that in the previous video. We said that this thing is Shwarz inequality, right? I think like back then I made a mistake, so sorry for that, because I said the opposite. I did the following like this. It's in fact like this, and you can just check by expanding everything, and you're going to get that this thing is just like sigma x square y symmetric is less than sigma x cube plus 3xyz, and as we said, like this thing is just sure. So we're done. Okay, so as you can see, this substitutions are very nice because they kind of also make you get rid of the condition, and they force homogenization. So yeah, substitutions are very important. Okay, so let's take another example to illustrate the importance of substitutions. Our third example is from Romania 2002. So in this question, we're given 3 ABC that are in this interval. They are between 0 and 1. And we're asked to prove the following inequality. Okay, so now the only condition we know is that the numbers are between 0 and 1. And this is logical because everything is under square root, so it should be greater than 0. And the 1 minus a should be positive as well. So that means that a should be less than 1. Okay, how exactly can you prove something like this? How can we get rid of this weird condition? They are between 0 and 1. If you look here, you might think of a nice if you change the variables, you can say this thing is x, this thing is y, this thing is c, so that they are greater than 0. But this is useless because you're going to get literally here 1 minus x, 1 minus y minus 1 minus c. So thinking about some let's say manipulation like this is useless. So what can we do? How can we really make everything beautiful? Is there a nice substitution just like the one we discussed for ABC equals 1? Well, in these types of questions, there is really not let's say a famous substitution. You need to figure out. Sometimes you might have a magical substitution that can kill the question and make it way easier. Here, can you think of such a substitution? It's really like magical here. Try to think about it. Alright, so the substitution actually, since we know the numbers are between 0 and 1, what does this remind you of? Do you know some quantity that's always less than 1 and like greater than 0? Well, there is like the trig functions actually, right? The sine, cosine, these are all between -1 and 1. If you restrict the angle, you can make it between 0 and 1. So for example, if you like make a cosine of x, then of course what's like the condition on x? You know that the cosine function here, like this thing is the one here, and this thing here is the like 0 for it. This is the cosine. So basically, if you just like take x between 0 and pi over 2, then yeah, like that works. So that means now you can just say that there exists x, y, z that belong to this interval from 0 to pi over 2, and basically it's like such that a is cosine x, b is cosine y, and c is cosine z. Okay, okay, this is like correct, of course. We have like cosine, 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 and that means we already like handle this condition. However, if you look here at these like inside, okay, if you make them cosine, you have like here root of pi cosine, and you're going to have root of 1 minus cosine, like the pi of that. However, something like nicer that you can do here. Here, if you have a cosine, here you have 1 minus cosine. 1 minus cosine, it's not really nice. What is nice, however, is 1 minus cosine square. Because 1 minus cosine square is sine square, right? So perhaps this is even a better substitution, because this will both implement this condition, like this condition, sorry, and will also make this very beautiful, because this thing will be just like sine square, pi of sine square. This thing will be pi of cosine square. So we're going to get something very nice. So let's change our substitution. We want a to be cosine x square, and cosine here square, cosine here square. Do we need to adjust anything here? Well, not really, because like if you have the numbers from 0 to 1, if you square them, then they are the same. So you can just do that. Okay, now this thing is way better, because now we can just like our inequality is the same as like sum. Oh, sorry, the root of cosine square, cosine square, cosine square is just the product of cosine. So it's pi cosine plus, or actually let me write all of it, cosine y, cosine z, plus this thing, as we said, 1 minus cosine square is sine square, so it's just product of the sine. And we need to show this thing is less than 1. As you can see now, we got rid of this condition, we got rid of like everything, even this now has become way nicer. So this is what we call a magical substitution. Okay, so now let's try to prove this generally. How exactly can you prove something like this? If you recall, this thing should be familiar to you, but not really. Like if you have 3 variables, if you have just 2 variables, cosine times cosine plus sine times sine, we already know that this thing is like a famous formula actually. That's in fact equal to cosine x minus y, right? Cosine x minus y is equal to this plus this. However, here the problem, we have a cosine z and sine z. So what can we do? Well, guess what? We know that the trigonometric functions like the cosine and the sine themselves, they are less than 1. So what we can simply do is the following. The LHS is less than, this thing is less than 1, and this thing is positive. So this thing is less than cosine x, cosine y. Same thing here. Sine is less than 1. So you can just say that this thing is sine x, sine y. And now this thing is the cosine x minus y. Of course, this thing is less than 1. So basically, now like we're done. Okay, again, here our like main idea was the magical substitution. Since we saw that here the numbers are between 0 and 1, we thought about trigonometric functions, and especially that if you look here, you have like 1 minus a trigonometric function is going to be really a nice thing. Not really the trigonometric function cosine or sine, but the cosine square is very nice. So this is exactly what we did, the magical substitution here, and we immediately like got a way easier question. So basically, that illustrates the idea of substitution, the importance of substitution. Sometimes we have classical substitutions like the xyz equals 1, and sometimes we need to do a more creative substitution. Each question, like sometimes you might have weirder conditions, you can always like think of other substitutions. It depends really on the question. There are some like some ones about the tan function. Sometimes you might do something like this: a equals tan. It really depends on the question. Each function has a special let's say characteristics. So like in each question you really have something special. If you know like there was a nice property, for example, for the tan. So let's say you know that some question, you know, a plus b plus c equals abc. Then you can define this a to be tan x and the same and so on, such that x, y, z like they form like angles of a triangle, or angles of a triangle, because we know that a plus b plus c equals abc. In the tan x plus tan y plus tan z is equal to tan x times tan y times tan z. This is correct when x plus y plus z equals 180 degrees, or like that means just here pi. So for example, this is also another like substitution idea that you might do in another question. So like as I told you, I cannot really tell you all these substitutions. You need to figure out in each question. If whenever you have like a weird condition, then you should immediately try to pick a suitable substitution. Of course, this comes from experience. Like when you're exposed to like these problems, each time you're going to see maybe like a new substitution. Alright, our last example for today is the following. We're given 3 numbers that are positive. They're all less than 1. This is one condition, and we know that their sum is 2. We need to prove the following inequality. Okay, so now if you look at this, you have a condition that their sum is equal to 2, and you know the numbers are less than 1. What can you do here? Of course, their sum is like all the numbers are less than 1, so that means these guys here are positive. So this is nice. Like for example, you can multiply by pi 1 minus a, no problem. You just need to show like abc is greater than a times pi 1 minus a. However, you still actually want to kind of get rid of the conditions, right? So how exactly can we do that here? One idea is to immediately go and homogenize, because you know here like you have a degree 1, here degree 0. So maybe if you multiply maybe like here by 2, and like you can just substitute sigma a here. So that actually I think works. But here what I wanted to illustrate for you is something even like neater here. What you can do in these types of questions, for example, they told you the numbers are less than 1, and you know the sigma a equals 2. And here if you look, the denominator is kind of not really nice. So one very very simple manipulation that you can do is, instead of dealing with like here a simple numerator and here an ugly denominator, do the opposite. You can just set x to be 1 minus a, and y 1 minus b, and z 1 minus c, and immediately now of course you have the opposite. So now a is 1 minus x. So now what you need to show is pi 1 minus x is greater than or equal to 8 xyz. And now the new conditions, you still know that x is less than 1 and greater than 0. But what you know now is that sigma x actually, you can think about it here, is equal to 1. So now you need to prove this, and you know that sigma x is equal to 1. So now if you look at this, how can you prove this? Well, guess what? You know that sigma x is equal to 1, so you can literally homogenize this easily. 1 is sigma x, so it's just going to be like y plus c is greater than or equal to 8xyz, which is true of course by AMGM. Okay, so basically here, my idea was sometimes you really need to spot these manipulations, these algebraic manipulations. They can make your life way easier. Okay, like this example might have been like also easy to deal with by just homogenizing, but sometimes you really need to catch these like algebraic manipulations. Whenever, for example, you saw here 1 minus a and then a, and you know the number is less than 1, you should always think about doing this manipulation. You can do it. There are other manipulations. Sometimes you might know ABC equals 1, and you don't really want to use that trick, a equals x over y, and so on. You can sometimes do this, make a 1 over x, and b 1 over y, and c 1 over c. We already illustrated this in like previous examples, in previous videos. So this is also another manipulation, let's say manipulation, algebraic manipulation. You're not really homogenizing immediately, but you're doing something that really make your life way easier. So you should always spot these kinds of stuff. Yeah, basically that's it. Alright, so basically today we discussed many important algebraic tricks. In the previous video we discussed the Ravi transformation, which is really a kind of just a technique to get rid of the triangle sides, side lengths condition. And in today's video we discussed many other techniques in order for us to get rid of the conditions they give us. So the standard technique that we have always used is the homogenizing technique. So for example here, example 1, you immediately can homogenize, make this thing degree 2 and this thing degree 1 easily by just like using the condition. So that was very easy, but we saw that in other questions this thing might be more difficult. So here homogenizing this might be like harder. We need to have kind of substitution that is nice to get rid of the condition. We saw the standard ABC equals 1 substitution. This one is very famous. Once we did it, we immediately killed the question at once, by sure. However, sometimes we might not have a famous say substitution. So you need to figure it out yourself from the conditions. Look, you know a number, for example, here. The numbers are between 0 and 1. You have this like 1 minus a. What can you think about? Well, one idea is to try trigonometric functions. They are very nice. They are indeed between 0 and 1. So exactly this is what we did. And not just trigonometric functions. We thought about cosine square or maybe sine square. They both like kind of work. So that also like helped us immediately like kill the question. Finally, we saw that not always we need to do really substitution. Sometimes it's really important for us to catch some algebraic manipulations. So changing variables, like for example, instead of working with a, let's work with 1 minus a as our variable. Here it's like made our life much easier. Sometimes, as we said, instead of working with ABC equals 1, let's work with the inverse of these, 1 over a, 1 over b, 1 over c. All of these like ideas are very important for you when you're solving like in general math Olympiad inequalities. Okay, so that finishes our algebraic tricks. We still have one final idea that we'll be discussing in our next lesson, and that is a normalization technique. So I hope you guys enjoyed today's video. Please like, share and subscribe to the channel and join the Discord server as well, and see you guys in the next video.